Testing 1, 2, 3. Alright, I guess we get started. Set up the environment real quick. So, what do I even have? Oh crap, I don't have. This is gonna be a little bit scuffed. I guess in the meantime, we can talk about the problem. The music is way too loud, I can't hear anything. Alright, that's better. Still too loud. So the lowest common ancestor is the lowest node in the tree, aka the first node that you would encounter going up the tree. That is an ancestor by virtue of being up in the tree, and the lowest one by virtue of being the first one of two nodes, so that's the common part. So what that means is that if you have two nodes, and preferably these two nodes are distinct from each other, then naturally at least one of them will have to have a parent. And once again, if you compare that parent with the other one, so long as they are distinct, then at least one of them would have another parent, so on and so forth. Each of the parents that we consider along the way will either have one of these two nodes as their descendant. That is to say, if we perform a membership test for the subtree starting at that parent node, for one of the two nodes that we're interested in, one of these two binary nodes, the result that we get back should be yes. Oh god. Hold on, I'm running into some problems. Okay. Let's see where we are with this. Maybe I have to relaunch this. That's a bit problematic. Oh, I probably have to relaunch VS Code. Oh. Well, I don't need Visual Studio right now. I just need Dirt, so as long as I have Dirt, should be okay. Okay, so let's get back to the analysis. Let's see. Okay, so let's see. What do we have? First of all, let's see what the external requirements are for this function. So let's say I have two nodes. I don't really need them to have any content, so let me write the tree node class real quick. They probably need a parent pointer, right? So they have to have a tree node reference that it can be known. Parent. And they have, it's a binary tree, so it also has a left child and it also has a right child. And what else? It has to have an empty constructor if we want to make it like that, so I guess we need okay. So these two are supposed to be part of a tree. So first we have to construct a tree. Let me dig up my old stuff real quick. Let's see. This is actually really nice. Alright, let's steal some of it. Right here we're gonna make a file. We're gonna call it tree.py. So here, what do we call it again? It's an addition? Sure. Why not? Okay, that should do it. We'll also override a toString. Sure, that's good of a representation as anything. Okay, so now I'm gonna import tree. Okay, so I'm not gonna do that anymore. What's gonna happen is I'm gonna take a bunch of values. You know what? I'll take both of them. And let's let's see. So we have 3, 9, 20. So 9, 20 are two children of number 3, which makes sense. This is index 1. If you double it, you get index 2. Plus 1 is no. So index 9. So the node number 9 has no children. And 15 and 7 are exclusively children of 20. That makes sense. If I change this node to, I don't know, 143, then 143 will be the child of node number 9. Let's try that again. Yep, that makes sense. And then, just for completeness, okay, not bad. Okay, so as for my use, right now I'm only looking for common ancestor, so it doesn't really matter what tree I use. I'm going to use this tree. Now, I'm going to have to implement value comparison to extract this identity, because otherwise I don't have a way to easily identify which node I want. So I'm gonna have to go back to tree and override something else as well. So for this one, I will use the values. Return val is equal to oh god, it's not a tree. How do I do this? How do I override? So there's a function called identical. If identical this and the other function, the other object. If it come true, then they are not identical, so then the other is not. It is also a function. This I check the class type. So now we know that they are not the same thing and they are both tree nodes, so we can just compare the value. But more importantly, oh god. Yeah, I'm not going to go that far. I'm only going to compare the immediate value. I'm not going to compare the subtrees. So I'm going to return at this point. Now I'll go to other background. Just this one now. I'm not going to make it complicated. I will also override the hash code. Okay, that should do it. Each node is unique because of its... If my comparison is not taking into consideration the value on the left and the right, then it should not be a part of the hash code, just the value. It requires two objects to hash. I guess if I'm only depending on the value, you know, I'll just put the other one randomly. Alright, so now I should have some way to say that a node is the same or different from another. So let's first make the two children from the root the same. What now? What do you mean? Oh, okay. Roots can be no, that's what it's saying. So let's do this. And assert that this will always return value. Okay, so yep, so it seems to be correct. Now if I change this to 4, it won't be correct anymore. No, it still is. I have to enable a search or something, if I remember correctly. Okay. So we failed. Let's change this back to 3. And we still failed. Okay, fine. Should move these up. $320. Oh, that makes sense because the root is 3. My bad. This is 5 and this is 3. So the assert is going through right now. And if I change this to 4, just to make sure the test is correct, the assert fails. So the comparison is working as intended, even though it's not how it's supposed to be. We can live with that for now. Alright. I also need a function for membership testing. Even though I'm not going to use it, it might as well have it. So it's going to be a Boolean function contains tree node. Just random node, I guess. So this one. So let's see if do we have a leaf function? I guess we don't. We should probably add it. Is leaf. No, that is leaf. Then we return that value being equal to, or just node being equal to this, I guess. Oh, good lord. Can't do that, so I'll have to do val equal to node.val. What do you mean? Oh, it's not in the tree function. Oops, I'm stupid. There we go. The tree should contain okay, and if it's not a leaf, then that means it has children. That means we return whether the children have it. So return either the first condition, which is node dot left dot contain. Wait, it's not a leaf. That means doesn't mean it has a left and a right. So I have to check. This is getting a little bit weirdy. Unwieldy. I need the result both from both the left child and the right child. What's a clean way to do it? Yeah, I can do this. Then we set file to the result of contains left of contains the same node. So much. What do you mean? I already asserted right here. This should not ever be false. Maybe note that left is different from left. Oh, right. My bad. No, that is different from. I'm not looking at the node. I'm looking at the. Let's call it target. This is confusing. Okay, so if my node is a leaf, then if it's the same thing, I found it. Otherwise, I haven't found it, and if my left is not null, then I search for the target in the left tree. This is weird syntax right here. I already asserted that it's not null, so it's kind of annoying to have to do that. Alright, so now if I have found it, then just return found. And the only time I ever reach this code is if I haven't found it. So that should be conclusive right there. That should do it. Okay, so let's go back to testing. Let's assert that my root contains a node, tree node, value 143. Okay, how about 142? There we go. How about 7? I'm convinced. Okay, so the basics are done. Let's actually work on the LCA problem now. Fortunately, because we have a parent pointer, the FCA problems is easily reduced to a variant of the margin linked list problem. So let's see. Let's see. What the heck? I want to have. Okay, let's just find the deepest one and see what happens. So this is. I kind of forgot what the tree looks like, so. How do I print a tree again? Print tree. Okay, so. So right now, 7 and 12 are on different branches. The first common ancestor is the root node. We can confirm that partially by asserting that the left branch contains. Which one is the left branch? The one that contains the earlier values of 12. And we can assert that the right branch contains the node that comes later. Okay? And because they are separate branches and they each contain 1, that implies that the first node that is the same, the common ancestor, is the root. So now, this should be equivalent to asserting that doing this. If we did this, then the two should be equivalent. So now, find LCA should be a function that returns a node reference into a node. Is it guaranteed that we always are going to have one? So this, whether this is going to be null. I don't think so. The existence of the common ancestor has to be true unless the whole tree doesn't exist. Is it possible that we're given 2 distinct nodes on 2 different trees? I guess that's possible, but I can just enforce that it doesn't happen. Alright, now that we're starting, I'm going to start a timer. Okay. So... we're gonna use the linked list merging problem, because effectively that's what this is. Each branch is going upstream along a deterministic path, and they meet each other at some point. That is to say, there exists a node along each path where that node exists on both branches, and the core problem is that each branch arrives at that node at a different time if they were to travel together. So what we do is, first we establish pointers. The first tree node, current 1, and current 2. Okay, so current 1 is going to point to node 1, and current 2 is going to point to node 2. Now what we do is while node current 1 has next, it doesn't have next parent, is that null, then we will advance here we go. And then we do the same thing for current 2. Oh, come on. It's 3 variables. There are 3 of them. Come on. Oh god, it's so stupid. Okay. So by the time that both of these pointers have stopped, they must be pointing at the root. And along the way, what we do is we increment the count. So do we start at 1? Do we start at 0? Let's think about it. If we start the root node, that means that we don't ever increment, and the length is how many? How many nodes do we want to say that there are? If there's only one node, if the node is already at the root, then the length of the list should be, we can encode it any number of ways, but because I've already named the length, I feel inclined to call it 1 instead of 0. Okay, so after we are done here, length will now count the number of nodes in each path. So we count the difference. Length 1, absolute value. Wait, we need to know which one is bigger, so we can't do this. Okay. What we can do is assign new pointers, I guess. So tree node long is set to length 1 greater than 2. If it is, then the long one is the first one, and it would point to node number 1. Otherwise, it would point to node number 2. And then short will be similar. Yeah, the logic should be the same task but different assignment. Should be fine. Right. So now that I have these two variables, what I want to do is I don't need to. I'm just gonna do the difference is equal to 2 minus 1 absolute. Okay, so now we apply there we go. So by now, should be equidistant from the end. So now we will find a common point while long is not the same as short, and we assume that there will be a common point because we said so. Long is equal to long dot parent, and short is equal to short dot parent. And then once we break out of this loop, presumably and they both should be pointing at the LCA. So what we do is we return one of them. Okay. Let's run the test. Okay. Some problems. 39. Oh, that's true. That's true. We have a problem. Wait, hold on. Do we have a problem? They have to meet before they reach the end, right? The only time. Yeah, they have to meet before they reach the end, so this should not be a problem. Let's try printing some debug messages. It might be off by one error somewhere. Most likely this one. Okay. Alright, let's try again. Long is 7, short is 12. I mean, that makes sense because one of them has to be long and the other has to be short. They have 0 difference. That means that they should start walking together. So if I were to bring this down, we should see their progress along the way. If we can pass this step somehow. Oh, the problem is we're making these nodes out of nowhere. They're not actual nodes in the tree, so this doesn't work. I have to actually retrieve the node from the tree. Okay, that's unfortunate. Okay, so it is equal to root.left dot left, I guess, because there's only 2 layers. And then this is root of right and right. That should be okay. For this example, I know that these nodes exist, so I'm not gonna complicate too much about node checking. Okay, so contain is no longer true because we moved them around. Node 1 is not at F1, so I have to change this. Okay. Okay. 45. Still the same thing, huh? And it's the first time to, it's not, hold on, let's think about this. This tree operation is not assigning the parent value yet, so I have to go in and fix that. Okay, construct binary tree. How do I fix this? Okay, I can change it here. If the left child pointer is assigned here, then the parent can also be assigned here. And similarly, that should do it. Okay, we're getting somewhere. Okay, we're getting somewhere. Okay, so now there's a problem with the fact that we're comparing them based on value. So I'm gonna temporarily enforce unique values, and then we can fix it later. There we go. Okay, so the only reason why we need to enforce unique values is because our equal comparison is limited to using value for now. If we were to fix it so that it fully and truly compares to subtrees and not just 2 nodes, then we should be able to do this even if they have duplicate values. Okay. So what's going on here? 3 and 3 at some point long and short got to the number 3 and 3, but they did not exit the loop because this comparison is now false, even though their values are the same. So not until we reach number 5, where it's actually the same node, that we exit the loop, and it would report the correct LCA. Okay, that should be it. Are there any edge cases to consider? I guess I should test the situation where one of them is a parent of the other one. So final no 3 is equal to, let's say, root dot left. So it should be a parent of node 1. So then we want to assert, we'll just assert that node 3 itself is the LCA between node 3 and node 1. I guess we can do the other side, but again, I don't see a reason to. The last case is if they are the same node. So if node 3 and node 4 are the same node, what happens? Assert that node 3 is the same as LCA 341, but we assert that node 4 is also the same as LCA 341. Otherwise, it doesn't make any sense. Okay, so there's a bit of a problem here. 46. Call from line 16, so we have a problem here. And the question is why? What's going on here that we have a problem with? Actually, I never tested the actual difference, so it's a bit premature to remove the printing stuff. So right here, before the difference, let's print out long. And then after the difference, we found that the difference is, and then we print these two again. Oh, I'm stupid. There we go. Okay, so maybe that was the only bug, but I'm going to be cautious and only comment on that from now. Okay, so it looks like all of the accessions went through, which is what we expect to be the case. So it never mattered whether this was 0 or 1 because we only care about the difference. So this could be set to 0 and it would not make a difference at all. But yeah, for the sake of conceptual clarity, alright, this should be it. Why am I committing like this whole thing? Whatever, doesn't matter. Alright. Let's do this. So we'll reuse much of the same test. But we're gonna do this recursively. So how do we go about doing that? Also, I should pause this. So recursively, if the left child contains one of the targets and the other target is contained elsewhere in this subtree, either at the root or on the other branch, then we have found the lowest common ancestor. Otherwise, we shall report upstream that we found one, not the other. So no, we're not gonna do that. We're gonna do bool and bool. Find CA. Or rather, has contains targets. 2. So these have to be real things so we can search for it. And if we ever, at some point, we ever find out that if we ever satisfy the condition, then at that point we set LCA to the current node. So what's the current node? This? Can we do that? Cannot do this. So let's see, what are we doing? We are inside a function, not a class, and we are given we probably need to add the last thing. Because we need to be recursive, so we need to know which node we're on. So, at this point, what we do is, if LCA is already found, then we don't do anything. And if it's not found, then we just return the root, because we have no more choice, right? So the assumption is that there has to be one LCA because we assume that both nodes is on the same tree. So the LCA has to exist, and if we haven't found it by the time we get to the helper function, then the only node left to be the LCA has to be the root. And if we have found it, then we return it. Seems good to me. And then, in our search, at some point when something satisfies the LCA condition, we will set the global tracker to that current node. So I will have to pass in a current. That should do it. The rest is just define what the LCA condition is. I also need the base case, so if current is a leaf, then I will return at least one of the two values. So now the question is, I guess I don't need to, right? So if the current.val is the same as node1.val, then I return true, false. And if current.val is equal to node2.val, then I return false, true. Right? That's it. In the event that it is not a leaf node, then I have to do the generic recursive logic. Right here. Until I satisfy the condition. Okay. So what is the recursive logic? The recursive logic is that I find this result somewhere and I find this result somewhere else. But first, if the LCA is already found, then we just simply return that it is found. Right? And then once we get to this line of code, we know that the LCA has not been found, which means if it exists at this point, then actually would it not always be the current node? It would, right? It would have to be the current node. That's why I wrote it here, because it is the current node. So the condition is that I find one node on one branch and the other node on the other branch. So if no the final left contains target is equal to current dot left dot, and I will throw this into the recursive call. Node 1, node 2, and the start node is current dot left. But I also have to worry about whether I have a current left or not. This is kind of annoying. But I know that I'm not a leaf node, so I know that I must have a left child or a right child, or both. So what I can do is, if my left node is not null, then I can recurse on the left. Okay. So if the left is not null, then oh, good lord. Oh, good lord. This is getting out of hand when you think about this. Okay, so the recursive call will return a tuple, so I need to do a tuple. Okay. The tuple is I'm gonna act on a node, and the tuple will tell me if that node contains the first one or the right one. The first one or the second one. What do you want from me? So now that we have that, what do we do with it? We want one of these to be true. Or maybe we should work with the false conditions first, and then the last condition is set if all of the cases where LCA cannot be found has been explored. But I don't think that's wise because it's more difficult to define that condition. Okay, I think I have it. So I have to break this into two variables. Oh god. And then this has to be left. Actually, we don't need to make it that challenging. I can leave it like this. And define these in here. Right? And what I do is if I either has node 1 or I has node 2, then it has mobile. Then I can set left contains target to be true. And that's all I care about. And then I do the same thing on the other side. then I check the conditions. It's a little bit too long here. I'm gonna rename this to curl so that it's shorter. Okay, so this will already be executed if we have a branch to explore, right? So there are three conditions for finding LCA. If any one of these is true, then we have found it. So we set boolean found LCA to false, and if any of these is true, then we have found it. Right? So now we just have to define these three cases. Case number 2, right as target, and case number 3, left and right as target. These three conditions, one of these three must be true. Oh wow, one of these three must be true if this is the LCA. So if left contains target and cur.var is equal to one of the other two. So I guess I should also do some preliminary work. So let's do the last one here. If we find it, then we set it to true, and if this is true, then we set this to that, and otherwise we just continue looping, right? Otherwise, we return our current status, which is left and right. So what's wrong with this? What this is saying is that this is always false. So why is it always false? I didn't set it to final, so it can be updated, right? Okay, so what if I flip this around? You're not going to complain anymore. But then you're going to complain about this one. No matter how I organize it, they seem to think that this left and right contains always false. But if I just don't assign it a value. Oh, I'm stupid. That's why. There we go. Okay, so this theoretically should work. I haven't tested anything. I don't even know if it... Okay. Hmm. Ah, dang it. Dang it, dang it. Okay, it still works. Let's be a little bit let's test it out, just make sure that it doesn't work. Okay, so now I have root 2. So if I were to set one of them to root 2, then the first assertion should be false. Okay, so I didn't account for that correctly. Or maybe I should do something like this. Okay, fine. I'll just give it completely new values. Starting with 20 should be safer, 21. Okay, so that should be safe. And then I will do that. Now it should not work. Okay, something's really wrong. I am asserting that whatever this returns. Oh, maybe my blanket case is doing something weird to it. Because if I'm not fighting, I'm just returning the root, because that's what my assumption is, right? But I shouldn't be doing that. If LCA is still no, I should return no. So I'm gonna go ahead and change this and return LCA no matter what. Okay. So now I'm gonna break everything. Nope. What is going on? I'm allowing for this to be null. which means at this point this can be null. And this is only ever set to be something if we ever proc this condition. But I am searching down the left branch and the right branch of the current node. So if I start from the root, then I should only be exploring one tree, right? I should only be exploring one tree, so I will never find the other one. This base case. Oh, I think I'm missing something. Fuck. I'm missing something. This situation is assuming that hold on, what is going on here? There is a situation where neither of these is true. But if that's the situation, then none of this happens, and I just simply return false, false, right? And if I return false, false, then at some point, no. Fuck me, dude. Huh. So the current situation doesn't allow me to tell my parent that I contain the target. This is so strange. How the heck is this tree containing that node? That makes no sense. Oh, because I'm running the wrong... oh god, I'm running the wrong test. Okay, prepare for mistakes. There we go. Okay. That makes sense right there. That makes perfect sense. Okay, so now we don't have to do this anymore. Okay, so this is not true, but that's down here. That is interesting. I don't care about this yet. Let's look at this base case. It appears as though it's trying to say that this base case is correct. That's crazy. Anyway, I gotta fix my logic here. This case is working because my base cases are catching the target nodes. The problem is I am never acknowledging that I found a node unless it's a leaf node. I'm only returning at each level whether my left node contains it or my right node contains it, not myself. So that's problematic, right? I actually don't need this much complexity. What I need is to return just one Boolean value. Whether I myself contains something. If I contain something, that's all that matters. I don't care which value I contain, because I can only contain one. That's all that matters. So, that's all that matters. And I will say that I contain target, not targets. Okay. Because I never get to a point where a single branch can contain two targets. The first time I encounter a situation where I have both targets within the same context, one of them has to be down to one branch and the other one has to be either the root or the other branch. So one branch never contains two targets. So these two is good, and this is also good, but I don't need to do this all this much. I just have to have a single Boolean. And this one is left contains target. And same thing here. This just has to be right contains target. Okay, so Yep, all of these conditions will still hold. And if it holds, if any one of them passes, then we set it to true. Once we set it to true, we then set the LCA. And the only time, and what do we return? We either return true or false. So we return left contains or right contains or curve is target. Doesn't matter where we find it, we will report that we have it. This way, when we encounter it along the way, we will update our understanding. Okay. So now when I enable this, we have a chance of making it work. Okay, not yet. Okay, let's print it out then. Let me okay. Let's run this first, failed it, and then let's print some stuff. What do I want to print? I think it's gonna be quite a bit of printing, so okay, let's see. Looking for 2 and 4. Okay. Currently processing 2. Left is true and right is false. So we found number 4, that's why we are saying that left is true and right is false. Based on the condition above, FCA is found true because we have we are processing node 2 and we found something on the left tree, so FCA has to be found. So why do we continue work? Yep, it is tree node 2, that's correct. But why did we change it to 1? So once we find LCA is not null, so we return true, right? We return true all the way up. Why are we updating it again? So let's see what happens when we return true. If we return true, oh, that's a problem, right? That's a problem. If we return true, then the left branch and the right branch will both continue to return true up the chain. The only time we should do this is this. We should only update once ever. There we go. We should only ever update once, and that's it. Okay, new cases to test. What's going on here? Let me remove this. Alright, let's see. 1, 2, 3, 4, 5, 6, 7. Looking for 2 and 2, okay. Left is false and right is false. Okay, so this is where the situation is a bit problematic. The assumption that I make is that, you know, one of these three cases is how you define the LCA. It doesn't account for the situation where the LCA is the current value both times. So it's just a matter of how, you know, strict I want it to be. The spirit of a problem is that these two nodes have to be distinct. I can easily account for this by doing this, and then it should take care of it. There we go. So I'm not going to change the logic of the LCA. I'm just going to have a shortcut like that. And now all of my test cases should be correct. There we go. Why would it not be true? 1, 3. Oh, okay. There we go. Alright. The last thing to do is clean up the signature if I don't want to pass the root in. But because it's recursive, I kind of have to pass the root in. Unless I want to have a function where I find the root of a tree and then use it as my... I actually can do that. So what I can do is remove this and keep the root management internal to this function. By having a function called, but I'm just going to do a quick routine. Current is equal to node 1 while... Oh, I don't have a parent pointer. How the fuck am I going to find the... If I don't have the parent pointer, I can't find the root node. I guess I'm just gonna use the parent pointer to find a root node. But not use the parent pointer to solve the problem. Yep, there we go. So I would make use of the parent pointer to find the root node because I have no other way to do it. But I will not use it to solve the problem because I want it to be a challenge. Alright, that's it. That's it for today. Took much longer than I wanted to spend, but we got there.